Everybody, and welcome to our first video in Unit 4, which is all about just very basic chemical reactions, especially ones that will happen in solution. So before we even get started, let's go ahead and just define what a chemical reaction is. So hopefully at this point in your chemistry career, you know what a chemical reaction is. And of course, this is the transformation into new substances. So that's why we write reactions the way that we write them, or we write equations the way that we write them. So for example, if I have water, or I'm sorry, hydrogen, and I react that with some oxygen, this is considered a chemical reaction because I'm forming something that wasn't there previously. I formed something totally new. So anytime I form something new, in that case, we call that a reaction. And a lot of times things aren't necessarily considered reactions because I'm not making something new. So a good example of something that's not a reaction, so I'll say no reaction, that looks very terrible, would be if I have salt that's dissociating in water. This is not an example of a chemical reaction because I didn't make something new. I just took those salt ionic substances and they dissociated, they separated into their ions. So in that case, that is not considered a reaction. I didn't make something that wasn't there previously. And we're going to talk more about that in this particular unit. And of course, in Chem 1 and in Chem 2, we talk about the very 5 basic types of chemical reactions. So there are synthesis reactions, there are decomposition reactions, there's single replacement, there's double replacement, and combustion reactions. So these 5 basic types of chemical reactions are basically like an umbrella for a whole bunch of different other types of reactions that we could see. So there's my umbrella, but these 5 right here help to differentiate between other different types of reactions. So in this particular unit, we're going to see a new type of reaction, which is an acid-base neutralization reaction. That's a type of double replacement reaction. So we see acid-base. Another type of double replacement reaction would be could be a redox reaction, or a redox reaction could also be a type of decomposition reaction or a synthesis reaction. So we're going to introduce 3 new reactions, particularly that occur in solutions, that are kind of more specific for each of these 5 very basic ones that we've already talked about. So like we said, these reactions that happen in solution, there's 3 types of reactions that can occur in an aqueous solution. And the first one is an acid-base neutralization reaction. So, of course, an acid-base neutralization reaction is what we're going to find when I have an acid that reacts with a base. So what particularly happens, though? What's the chemistry behind that? An acid-base reaction involves the transfer of a proton, which another way you could say a proton, it's basically just a hydrogen ion, right? Because a hydrogen ion only has 1 proton. It doesn't even have an electron because it has a positive 1 charge. It involves the transfer of a proton, which is a hydrogen, between chemical species. So here's a nice example of an acid-base reaction. So I have an acid. And typically your acids are going to have a hydrogen in the front. So you might already be familiar with this, but this is hydrochloric acid, HCl. So here's my acid. And I'm reacting this with a base. Now we're going to talk a little bit more about acids and bases in another video. We're just kind of going over the very basics first. But in this case, you'll see that the proton in my acid is getting transferred to the anion of sodium hydroxide, right? So this proton is getting transferred to the hydroxide to make water. So a lot of times the products of an acid-base reaction is water, one of the products, because I have that transfer of that proton. And my other product is generally some salt, where it's not just sodium chloride that's a salt, but a salt is usually any combination of metal and some non-metal. So some type of ionic substance is what I form. This looks like a double replacement reaction, and it is. But more specifically, this is what we call a neutralization reaction. So we are transferring a proton from one species in the reactant side to another species in the reactant side. So typically, your hydrogen ions, we'll write this, and your hydroxide ions combine to form water. And that's a key indicator that you know that a neutralization reaction has occurred. I actually want to go back here and talk about some ways that we can identify how do we know a chemical reaction has happened, right? So what are some pieces of evidence that we know a reaction has occurred? Some of the most obvious ways that we say is that if we produce a gas, if there's a gas that's produced, we know that a chemical reaction has changed, that a chemical reaction has occurred. If I have a color change, a lot of times we know that a chemical reaction has occurred. You might also see a pH change. And this in particular lets us know that a neutralization has occurred. If we have a pH change in between or before a reaction happened versus after a reaction happened. We might also see some sort of heat change. So whether heat is absorbed or if it's evolved, if it feels hot or cold, right? That could also tell us whether or not a reaction has happened. These are generally some of the most primary ways that we could tell. Oh, I forgot one. If we produce a solid precipitate, we produce a precipitate. So I'm making something that wasn't there before. In this case, the gas wasn't there before. That's a piece of evidence we have that a reaction has occurred. A color change, that wasn't there before. If a precipitate has formed, we know that we've had a chemical reaction. I just wanted to go back to take a second to talk about that. So our first type of reaction in solution is acid-base. Let's go ahead and talk about the second type of reaction that could occur in solution. And this is what we call an oxidation-reduction reaction. And this is also known as a redox reaction. And I'll write that down here in a second. But a redox reaction involves the transfer of electrons. So not protons here, we're talking electrons between chemical species as indicated by a change in the charge or oxidation number of an atom, or we'll say element. So let's get the pen out here, but we also call oxidation reduction reactions redox reactions. It's a lot more simple than saying oxidation reduction all the time. So just remember that that's our shortened version. In this case, we have a change in charge between the reactants and the products. So a nice example of a redox reaction is this one that's below. I have silver with a +1 charge. So here we see silver has got a charge of +1. Here, copper has no charge. So we say that its charge is 0. On my product side of the reaction, silver now has a charge of 0. So notice how silver goes from having a charge of +1 to 0. That is how we know a redox reaction has occurred. It goes from having a +1 charge to a neutral charge, whereas our copper goes from having a neutral charge to having a +1 charge. When I have these species that change in their charge or they change in their oxidation number, we know that to be a redox reaction. And that, of course, is a change of electrons. So if silver has a +1 charge here and it becomes neutral, we know that this silver gained an electron. Gained an electron. Whereas here, if copper is neutral and it's going to a positive charge, we know it has lost an electron. It's losing a negative thing, so it becomes positive. And we're going to talk more about that in our redox video, because again, I'm just kind of going over the preview of each of these 3 types of reactions we're going to talk about. So in solution, we can have neutralization reactions, we could have oxidation reduction reactions or redox, and we could also have precipitation reactions. And a precipitation reaction is when you form a precipitate, where a precipitate is a solid material. So when we mix ions in aqueous solution to produce an insoluble or partially soluble ionic compound, which we know as a precipitate. These are great examples of double replacement reactions. So again, another double replacement here. I should have said a lot of times your redox reactions are going to be single replacement. Not that you need to know that, because again, single replacement's the more broad name for that. You just need to know it as a redox reaction. So in this case, for a precipitation reaction, we have 2 aqueous solutions. So notice here, I have sodium sulfate is an aqueous solution. And I combine that with another aqueous solution of lead 2 nitrate. When those 2 react together, I form an aqueous solution of sodium nitrate, but I form solid lead 2 sulfate. So because I'm producing that insoluble product, that precipitate, that's how we know that a precipitation reaction has occurred. So I form a solid precipitate, which I guess I don't have to say solid. It's kind of redundant because that's what a precipitate is. But yeah, that's how I know precipitation has occurred. And one way that you can tell what's soluble or not soluble, in Chem 2, we talked about all those solubility rules, right? You don't have to really memorize those solubility rules because there's certain ions that are always soluble in water. They will always be aqueous. So always soluble means they'll always be aqueous. Those salts are anything that contains the sodium ion is always soluble. Sodium phosphate would be aqueous. Sodium oxalate would be aqueous. Sodium bromide is aqueous. Anything that contains potassium ions is always soluble. Ammonium ions and nitrate ions. So if you're given some sort of reaction and you have to identify the solubility of the products or reactants, if they have any one of those 4 ions in it, you know that it's soluble. And if it does not have those in it, we will assume that it is insoluble. College Board does not have you don't have to go that in detail with it, because you'll always have some combination that contains one of these ions in there. You're going to see lots of practice with that, so you'll kind of understand what I mean there. So those are the 3 different types of reactions that we'll see, particularly in solution. Before we dive in and talk about these reactions even more so, let's go ahead and talk about the nature of aqueous solutions. So in Chem 1 or Chem 2, we actually never really defined what aqueous means. So let's just take a second here and do that. And I think you already know what it means. But aqueous sounds a lot like aqua, right? And that means it's dissolved in water. And water is also known as the universal solvent. That means that water dissolves most substances. And that's because water is very polar, and most substances are, in fact, have some polar character to them as well. So water dissolves most things very, very well because water itself is very, very polar. Anything that's aqueous is dissolved in water. And one way that you can characterize solutions is based on their conductivity. So is based on conductivity. So we know if a solution is very conductive, if it is a little bit conductive, or if it's not conductive. That conductivity of that solution tells me quite a lot about the substances that comprise it. So something that is a strong electrolyte, this means that this solution completely, or that solid, I should say, that ionic solid, completely dissociates in water. So let's get that down here. Strong electrolytes completely dissociate in water. And as a result, these are highly conductive solutions. So something that would be an example of a strong electrolyte is something that is very, very soluble. So anything that has any of those ions that we talked about before, any of these would be very, very soluble. And that's because they dissociate very, very easily. Strong acids and strong bases, which you really don't have to know that just yet because we're going to talk more about that in the acid-base unit. But they also completely dissociate in water. So what does that mean? That means that every single particle will break up into its ions. So if I have NaCl solid and I put that in water, that completely breaks up into its ions. That's what we say is complete dissociation. Every single salt molecule dissociates. If I have hydrochloric acid is actually a gas at room temperature. But again, this completely dissociates. Every single hydrogen and every single chloride ion will break apart. I could see that in this solution down here. So notice I have a 1-to-1 ratio of positive to negative, 1-to-1 ratio of positive to negative, same thing here. This must be something like NaCl. This particular substance cannot represent something like Na2O because there would have to be 2 positive ions per every 1 negatively charged ion. So that's not represented here. This has to be like NaCl or HCl because it's a 1-to-1 ratio. But notice every one of those has dissociated. Because I have these charged particles, electricity can flow very readily in a solution. So you'll see that this light bulb here is very, very bright. And that's because electricity is able to flow between the solution because it has all of those charged particles. Weak electrolytes, on the other hand, do not dissociate completely. They'll dissociate, but they're not going to dissociate to the extent that a strong electrolyte does. So these only partially dissociate in water. And as a result, these are partially conductive. So some examples, I have barium fluoride. I have weak acids and weak bases. These ones do not totally dissociate. You are going to find with these that some of your barium fluoride molecules stay together. So right here, look, here's a BAF molecule. And actually, I don't like this as much because this is 1 to 2. It must not be representing BAF2. Maybe this represents something like, let's see if I can think of something here. Maybe like aluminum phosphate. That's a 1-to-1 ratio. Some of them stay together. And so you see here, 2 of them stayed together. And these ones right here dissociated. Some dissociated, but some stayed together. So as a result, only some electric current can pass through the solution because I only have a few positively and negatively charged particles. Only these can allow electric current to flow through. So this particular bulb, not as bright, right? This one's really, really bright over here. But the partial or the weak electrolytes are not very bright. You're not going to have a lot of electricity that flow through because there's not a lot of charged particles. Non-electrolytes, of course, which I'm sure you can infer, means that they don't dissociate at all. They do not dissociate in water. And as a result, they do not conduct electricity. So some examples, right? Sucrose. Any sort of molecular compound tends to not dissociate. And that's because they are held together by covalent bonds. We can't break those covalent bonds in sucrose. We can probably break some of the intermolecular forces, but we're not going to break the covalent bonds to totally split up sucrose. So sucrose has a formula of C12H22O11. And if I have solid sucrose, it's supposed to be an S right there. This solid sucrose does not dissociate. This sucrose dissolves in water. So dissociate is not the same as dissolving. Dissociating means that it splits up, splits into any ions. Whereas dissolving basically means that they mix together. So although sucrose dissolves, it does not dissociate. This does not have any ionic bonds. Water does not have the ability to form those ion dipole intermolecular forces of attraction, and therefore I can't break those covalent bonds. So because there are no charged particles, because every single molecule stays together, this will not conduct electricity. This light bulb is off, right? So if I have a sugar solution, sugar will not conduct electricity because there are no charged particles in that substance. So notice all of these are together, all together. We have no charged particles, some charged particles, all charged particles. So we'll say all charged, some charged, and here none are charged. That is going to wrap up this video. I hope that makes a lot of sense. I think it is pretty self-explanatory. I think you'll find this unit relatively easy. I think it's pretty straightforward. Yeah, so I'm excited to dive into each of those 3 reactions with you as we progress through this unit. So if you have any questions, please ask me, let me know. Otherwise, I will see you in the next video, which is all about precipitation reactions. Bye.